all of topic 11 has to do with like measuring for when we do things in labs. Okay. So it has to do with measuring, calculating, and processing data. And the reason that we're starting on this is because when we come back in January, all of you guys that are SL, you guys are going to start the process of developing what we call your independent investigation, where typically you would find a research topic and kind of design a lab to test something, and you'd record your own data, and then you have to kind of put it in tables and make graphs and analyze it, and you have to write kind of a research paper type thing on it. You still have to do that. The only thing is because we're not here in person and you can't collect your own data, we have to get a little creative. And so there are some options that you can do things virtually. There are some, you can use like lab simulations and virtual labs online, or you can use different scientific databases and search for data that you can use to interpret in a different way than maybe what they did. So you can't do like the exact same thing that somebody already did, but you can take their data and then interpret it maybe to answer a different question that you put in your research paper. So what we're starting off with today is kind of some of the information that you need to know when you're arranging your data and when you're discussing it in your report, and some of the different things that you'll have to do with calculations. And so we're going to kind of go through, we're only going through 11.1 today. The other parts, we're going to go to 11.2 next week, but 11.2 is not in your notes. It's going to be separate. And then the 11.3 section is not till later. Okay, so really just this first part is what we're focusing on today. So kind of the first thing on here is these new terms, absolute and percentage uncertainty. So uncertainty just means that when we measure things in the lab, measurements are not exact, okay? Because all of the tools we're using are man-made, okay? So uncertainty is like a fact. It happens when you measure things in lab and in science. And so in a way for us to kind of say that we know there's an uncertainty, they came up with this method of when we record numbers that we've measured in a lab, I don't just write the number. So for example, this balance right here, it's reading 16.43 grams. But when I write down in my data table or in my report what the mass is, I write the value, but then after it, I have a plus minus, and I have what we call an uncertainty. This is an absolute uncertainty. An absolute uncertainty means that it's part of with that measurement, it's not a percentage. And so but these balances are digital. So anytime you have something digital, and it could be an electronic balance, it could be a stopwatch, it could be a digital thermometer, anything like that that's reading out the number to you, then your uncertainty that what you write at the end for the plus minus, it's always using the smallest scale division. So you have to look at your piece of equipment. And so in this case, on this balance, the numbers are read to the hundredths place. So they have 2 decimal places. So that means that our uncertainty has to read to 2 decimal places. So it's plus or minus 0.01 grams. Okay. And then if I wanted to change it to percent uncertainty, I can actually that requires a little bit of a calculation. So for percentage uncertainty, the way I calculate it is I do my absolute uncertainty divided by the actual measured value that I got. And then because I want a percent, I multiply it by 100. So the reason that you're going to have to use these is because these uncertainties, when you measure things in lab and then you do calculations, every time you calculate something, you have to carry the uncertainty like through the calculation. And so using these absolute uncertainties and percentage uncertainties is going to come in because you're going to have to add numbers or subtract numbers or, things like that, or multiply or divide. And then depending on what operation you're doing, the way that you combine your uncertainties is different. Okay. If you're measuring with analog things, and analog is like anything you have to read. So it could be a graduated cylinder, like in this picture. It could be a thermometer that's not digital, just a regular thermometer. It could be a ruler or a meter stick, okay? Anything like that you have to read like with your eye to measure, that's analog, okay? And so for analog, the way you figure out the uncertainty is a little different because This requires a little bit more human interpretation because we're reading it with our eye. And so it's a little less uncertain because it's plus or minus half of the smallest scale. And so if we look, for example, if I look at this graduated cylinder, the little tick marks on this measurement are going by ones, okay? Because I see 40, and then I can see there's like all the little tick marks all the way up to 49, and then there's the 50. So it's counting by ones, and then when I divide 1 by 2, I get a half. And so that's why the uncertainty on this is plus or minus 0.5, because 0.5, that's half, and it's half of 1. So if I wanted to write down the whole measurement for this number, I would write 43, and notice I do have to put 43.0, even though I think it looks like it's right on the line for 43. I have to record to the 10th place because that is where my uncertainty is. My uncertainty is to the 10th place. They always have to match. They should have the same number of decimal places. So that's how I would record the measurement for this volume. And then to calculate the percent uncertainty, it's the same process. I do the absolute uncertainty divided by the measurement times 100, okay? So the main difference here is that digital things are gonna give you better precision because their uncertainties are gonna be a lot lower because they're digital and you're not relying on your human eye to read it, okay? Qualitative and quantitative data, I'm not gonna spend a lot of time on this just because this is something you've seen in science classes before, but they're both important. What we need to know, quantitative means that it comes from measurements, anything with numbers, measurements, those are quantitative data. And quantitative data always has what we call random errors. Okay, we're gonna talk about that in just a second. Some examples of quantitative data: mass, volume. Other ones might be temperature. You might measure the pH level. You might time something and measure the time it takes. Okay, all those involve numbers and numerical data. Qualitative data is going to be things that are descriptive. So they don't have numbers, non-numerical, they're observations, not measurements. So examples could be if something changes color, if a gas is produced and you see gas bubbles. It could even be a description. So maybe you're not measuring the temperature, but maybe you feel something getting hotter and you're going to describe that, okay? It could be that you see light given off, okay? Or smoke produced. All those things are qualitative. So when you record your data, both quantitative and qualitative, you want to make sure you have it in a table. So this is a good example for a table. You want them to be organized. You want them to be labeled. For all the quantitative data has to have units and uncertainties. So if you notice right here in this first column, they've told us what they're measuring. So the first line, it says initial volume of NaOH, and it is after the actual title, then it has the uncertainty and it has the units right here. So that's important that you always list the quantitative data with the units and uncertainties because that you're graded on that, like as part of your IB grade. If you don't have it, then they'll knock you off on points. And then you want to make sure it's recorded to the appropriate precision. What that means, if you look at all the numbers here, all of them are recorded to 2 decimal places because that is what the uncertainty goes to, is the hundredths place. So even though there are zeros on some of them, they're still all to the same decimal places based on that uncertainty. And then qualitative data, we also put it in there. It's just, by itself, it doesn't need obviously uncertainties and units because it's not a number, but it's still in here because both of them are important. Okay, the next part talks about 2 different types of errors, okay? Random errors, and you have to know the difference because you have to be able to address them in your write-up. So random errors are really like what they sound like. It's random. They're caused by unpredictable changes. And it's an equal probability of the measured value being too high or too low. So it's random. You might have a few measurements that are too high, a few measurements that are too low. And it's caused by things like changes in the environment, like maybe the room temperature changed. You can't control that. It could be you misinterpreting the reading on something. It could be, this is the biggest one that we usually have, is insufficient data. Insufficient data means that usually you didn't complete enough trials to collect enough data. Because random error, you can reduce it. You cannot eliminate it. So like right here, it says they can't be eliminated, but you can be reduced by conducting repeated trials. They like to ask that question about like, how can you reduce random error? And the answer is almost always conducting repeat trials or doing repeat trials. Because the more trials you do, the better your average data is going to be. And so you're going to reduce those random errors. The other way you can try to reduce them is you can use precise apparatus. So instead of using like a beaker or a graduated cylinder to measure volume, use a volumetric pipette or even a burette, something that's going to have a smaller scale on it so that you have less uncertainty, okay? Systematic errors, on the other hand, these are the ones that you actually can fix because these occur because of a flaw in your design of your experiment or your equipment. So on this, the difference is your data, it's either all going to be higher or mostly higher, or it's going to be mostly lower. It's not random, like there's not some high, some low. It's most of them are going to be consistently higher or consistently lower because there's something wrong with the experiment or the setup, okay? One of the key things here, this one, systematic, cannot be reduced by repeating trials. That's only random error. But you can fix if you fix the flaw in your design, then you can fix the systematic error. So you can correct what's wrong with your experimental design. So some examples of systematic errors, anytime you do experiments where you're measuring temperature, heat loss is one of the biggest ways that you can have systematic error. If you don't have insulated containers, then heat loss is going to affect your values that you measure. So a lot of times when we measure what we call enthalpy, which is a version of energy, you're usually measuring temperature changes, and so heat loss is a systematic error. When you're doing a chemical reaction, if you lose product, so that could be something like you didn't scrape it all off the bottom of a beaker to measure, or more likely, if you have something where a gas is produced, if you don't have a sealed container to collect the gas, then you're going to lose that product, and that's going to affect maybe your end results. If you do a titration, we just talked about titrations in topic 1 towards the end. We want to always get to that end point where we see the color change, but sometimes we overshoot the end point and the color change goes too dark, and that's a systematic error. You'd have to go back and correct it and redo another trial to time it better and not overshoot it. If you're measuring volume, reading from the top of the meniscus, because you should always read from the bottom of the curve on the meniscus, okay? And then if you're using a digital balance, maybe you put something on it to measure the mass, but you forgot to hit 0. So that throws your number off, because maybe now if you didn't hit 0, maybe all your numbers are going to be really high now for the mass measurements. But all of those are fixable by going back and correcting, the other thing. You can zero the balance. You can start reading from the bottom of the meniscus. You can do another titration and stop it when your endpoint shows the color change right away. You can add a container to collect the gas in. You can use an insulated container that's got like styrofoam. So those are all things you can correct, whereas random errors, you can't. All right, so the last couple sections on here, what I'm going to do is I'm going to recommend that you make sure you watch the recorded videos on Canvas, because they go through how to work through this calculation, because really what they're showing you, propagation of uncertainties, this is where I was talking about we have the absolute and percent uncertainties, and we have to carry them throughout a calculation. So they're going to walk you through how to calculate what we call the enthalpy change, which is, there's an equation and they talk about it in the video. You use this equation, and so it involves multiplication, okay? And so when you multiply or divide your values, in order to propagate your uncertainty, you have to add the percent uncertainties. So they're going to show you that you're going to have to convert all your uncertainties to percentages, then add them up before you get to the end. If you're doing addition or subtraction, it's a little easier because you just add the absolute uncertainties. So when you go through this calculation, they're going to show you both. They're going to show you, because you're going to have to subtract numbers, because if you look here, see how this is 0.5 and this is 0.5, but this one's 1.0? That's because these were both measured. We measured the initial temperature of the water, and then we measured the maximum temperature of the water during the experiment. And so our thermometer had an uncertainty of plus or minus 0.5 degrees Celsius, because we were probably using an analog thermometer. But here, this is the change in temperature. That means that we had to subtract to get that value. So the first one I did 26 minus 18.5. That's where the 6.5 came from. So anytime you add or subtract numbers, you add the absolute uncertainties. So that's why up here at the title, it's now plus or minus 1.0, because I had to add these 0.5s together when I subtracted their values. So adding or subtracting values, you add the absolute uncertainties. Multiplying or dividing, you add the percent uncertainties. So they are going to work through that whole problem in the recorded video that's already on Canvas. And then the last thing is percent error, and this is also on there too. Percent error we're using to measure accuracy. So when you do your lab, they're going to tell you in your like analysis and conclusion area that you need to calculate percent error for whatever your research experiment is. Because if your percent error is higher than the total percent uncertainty for your experimental calculations, then that means that you had systematic error. So if percent error is higher than percent uncertainty, you have systematic error and you need to go back and see if you can fix your experimental setup somehow. If your percent error is lower than your percent uncertainty, then you don't have systematic error, you just have random error. And really the only way you can try to make that better is by saying to do repeat trials, okay? But that's what they'll do, is they like to do questions like this where they ask you to calculate maybe something, and then it says suggest possible errors and improvements to the method. So if the errors are, you have to use the terms random and systematic. So if you say there are random errors, then you could say more repeat trials, could help that. If you calculate it and the percent error is higher than the percent uncertainty, then you should say there's systematic error because the percent error is not within the uncertainty range. And maybe you would say, depending on what the lab is, if it's something with temperature, you would say maybe insulate the container. If it's something with a gas, you might say collect the gas in a sealed container. So it's going to, how you fix it is going to depend on what exactly you're doing, but there should be a way that you can adjust your experimental setup to fix it, okay? So that, I believe, is it.